Today, we're going to journey across the cosmos and explore one of the most fascinating phenomena in astronomy, stellar evolution. Stars, the brilliant beacons in the night sky, are much more than static points of light. They are dynamic, ever-changing entities. From their birth in dense clouds of gas and dust, to their spectacular deaths as supernovae or serene transitions into white dwarfs, neutron stars, or black holes, stars tell the story of the universe itself. Let's dive into this cosmic life cycle and uncover the secrets of how stars live, evolve, and ultimately fade away. Stellar evolution. Stage 1 begins in interstellar clouds, also known as molecular clouds, which are massive, spanning tens of parsecs. They are rich in hydrogen, with small amounts of helium and trace elements. External triggers like shock waves from nearby supernovae or collisions with other clouds compress the gas, increasing density. Gravity begins to take over, pulling the cloud inward and starting the journey towards star formation. Stage 2. As the cloud collapses, it fragments into smaller pieces. Each fragment is massive enough to eventually form a star or a system of stars. During this phase, the fragments heat up as gravitational potential energy converts into thermal energy. Stage 3. Eventually, the collapse reaches a point where fragmentation ceases after tens of thousands of years. Fragments shrink to the size of a solar system and are about 10,000 Kelvin. At this point, the density and temperature are high enough that the fragments resist breaking into smaller pieces. Stage 4. The core of the fragment becomes a protostar, an object that shines not because of nuclear fusion, but due to the heat from gravitational contraction. The protostar continues to gather material from its surroundings, growing in mass, about 100,000 years after the fragment formed. The protostar is getting hotter and hotter, reaching temperatures around 1,000,000 Kelvin. The protostar can now be plotted on the HR diagram. During this stage, protostars are surrounded by a disk of gas and dust. This disk can later form planets, moons, and other objects in a star system. Protostars are unstable and often release energy in bursts as they accrete material. This portion of evolution is often called the T Tauri phase. Stage 5. As the protostar evolves, its temperature and pressure increases. Over time, contraction slows because gravity struggles to compress the hot protostar and it begins to stabilize. The gas is completely ionized, but the nucleus is not yet hot enough for nuclear fusion. Stage 6. When nuclear fusion ignites at 10 million Kelvin, the protostar becomes a newborn star. This marks the beginning of a star's life as a self-sustaining object. Fusion provides the energy to counteract gravitational collapse, achieving a delicate balance that allows the star to shine steadily. The star is now a similar size and mass to the Sun, but is a bit lower in temperature, causing it to be less luminous. Fragments smaller than the fragment that made our Sun take nearly 1 billion years to form, while larger ones take about 1/50th of the time. The end result of all fragments, however, is the main sequence, the longest and most stable phase of a star's life. Here, the core fuses hydrogen into helium, releasing energy that radiates into space. Failed stars and brown dwarfs. Not all protostars become stars. If a fragment is too small to ignite hydrogen fusion, it becomes a brown dwarf. These objects are often called failed stars because they lack the mass needed to sustain nuclear fusion. However, brown dwarfs still emit faint infrared radiation due to residual heat. Stage 8. When a star exhausts hydrogen in its core, it leaves the main sequence and becomes a subgiant, burning hydrogen in a surrounding shell, 10 billion years after it entered the main sequence. As the core contracts, the outer layers expand, and the star transforms into a red giant, growing to hundreds of times its original size. The star is no longer in stable equilibrium and is far from the main sequence. Stage 10. Eventually, the core temperature rises enough to ignite helium fusion, producing carbon and oxygen. This is called the helium flash in low-mass stars. The star stabilizes for a brief period on the horizontal branch of the HR diagram. Stage 11. Then the star expands again and returns to the giant branch, where it continues shell burning. Low mass stars die differently. Stage 12. Low to medium mass stars eventually shed their outer layers and become so hot that their UV radiation ionizes the inner parts of the surrounding cloud, forming a stunning planetary nebula, often shaped like a ring or bubble. Stage 13. The core remains as a white dwarf, a dense Earth-sized remnant supported by electron degeneracy pressure. White dwarfs can also be naked in space. Stage 14. Over billions of years, the white dwarf cools and becomes a black dwarf, which is essentially a cold, dark stellar corpse. It remains the same size because gravity is unable to compress the body any smaller. White dwarfs often undergo a nova, where they become 10,000 times brighter for a few days and then return to their normal brightness. These are results of accretion disks forming in binary systems, where the inner part of the disk becomes hot enough to emit an enormous amount of light in multiple wavelengths. This can happen multiple times in a white dwarf's lifetime. High-mass stars and supernovae. High-mass stars leave the main sequence once they run out of hydrogen and become red supergiants. Supermassive stars are able to fuse carbon, oxygen, and even heavier elements, and the rate of burning in their cores evolves. The core eventually changes into iron, which is the most stable element, acting as a fire extinguisher in the sun's core. Equilibrium is destroyed, and the star collapses as gravity overwhelms the outgoing pressure. The core eventually becomes so dense that protons and electrons are crushed together to form neutrons and neutrinos. Then, the core rebounds and explodes in a supernova, scattering heavy elements into space, enriching the interstellar medium. There are two different types of supernovae. Type 1 supernovae result from a thermonuclear explosion of a white dwarf in a binary system, while Type 2 supernovae are caused by the core collapse of an extremely massive star. These differences lead to observable variations in their properties, making it possible to distinguish between these two types of supernovae. There are remnants of supernovae all over our galaxy. One example is the Crab Nebula, which has been famously photographed by the Hubble Space Telescope. Formation of the elements in stellar evolution. Scientists have identified 118 elements, ranging from hydrogen, the simplest, to organocin, the most complex. Elements exist as isotopes, which share the same number of protons but differ in neutrons. Earth hosts 81 stable elements and 10 naturally radioactive ones, which are rare due to their slow decay over billions of years. Artificial radioactive elements, created in labs, decay much faster and are extremely rare. Hydrogen and helium, formed after the Big Bang, are primordial, while heavier elements originate from stellar nucleosynthesis. In stars, nuclear fusion processes like the proton-proton chain and helium burning create these heavier elements over time, which are then released in supernovae. Neutron stars, pulsars, and gamma-ray bursts. Neutron stars are incredibly dense, with the mass of the sun compressed into a sphere about 20 kilometers across. They are the only remaining object from supernovae and contain neutrons packed together. If they spin rapidly and emit beams of radiation, they appear as pulsars. Also, gamma-ray bursts are extremely energetic events that last milliseconds. There are two models for their cause. One model is the merger of two neutron stars in a binary system. The other model is a flared supernova, or hypernova, where the core collapses and creates a black hole instead of a neutron star. According to stellar evolution theory, black holes are the result of stars that exceed 25 times the mass of the sun. Once the remaining core exceeds 3 solar masses, gravity wins the battle and the core collapses forever. Gravity eventually becomes so strong that not even light can escape. Black holes are much rarer than neutron stars because of the stellar mass they require. To end, stellar evolution is a reminder of the universe's dynamic and interconnected nature. Stars are not only the architects of the cosmos, forging the elements that make up everything from planets to life itself, but they also inspire us with their grandeur and impermanence. By studying stellar evolution, we deepen our understanding of the universe's past, present, and future. Thank you for joining me on this exploration of the lives of stars. I hope it's left you with a sense of wonder about our vast and ever-changing cosmos.